Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video we're going to continue talking about bending strength for wood, and we're going to finish up by talking about lateral stability factors now for glulam. In the previous video we talked about all the cases where we can consider KL equal to 1 for lumber, and then we also said if we don't fit those criteria for lumber, then we can use this method, which is the general method for calculating KL for glulam. So this applies really to both. Just like in lumber, there is one category for criteria where we can automatically consider KL equals 1, and that is if the depth to width ratio of a glulam beam is less than or equal to 2.5 to 1. So if my depth to width ratio is less than or equal to 2.5 to 1, I mean, this is a piece of lumber, my glulam depth to width ratio, total depth divided by width, is less than 2.5, then I can automatically consider that KL equals 1, as long as I'm still providing lateral supports at the points of bearing that will prevent lateral movement and prevent rotation at those points. And that is the only category where it's automatic. For every other beam, like for this one, where certainly depth to width is a bit greater than 2.5 to 1, I'm going to have to actually calculate KL using this method. And even though we're calculating KL, we still need those lateral supports at points of bearing to prevent lateral movement and rotation. And basically, we're going to have 3 different cases for KL, depending on a parameter called the slenderness ratio, which is similar. I mean, it's analogous to the slenderness ratio that we had before, CC, remember, which was slenderness calculation for compression buckling of columns. In this case, we're going to have CB, which is a slenderness ratio for lateral torsional buckling of beams. Okay, so first we have to calculate the slenderness ratio. It's a pretty simple calculation. It looks kind of similar to the one that we had before, but instead of just being length divided by the cross-sectional dimension in the direction of buckling, here we have a square root of LE times D, which is depth, divided by B squared. Okay, so we have LE, which is an effective length. This is similar to what we had before for compression buckling, where we had an effective length, which was a K times an L. This one is a different effective length, and there is still a K, but instead of getting the K from the boundary conditions like we did for compression, and we had that table in the appendix to the standard, here we're going to determine that K basically from a table, and we're not actually going to even bother to call it K. So we're going to determine LE based on some tabulated values in table 7.5.6.4.3. And this LE is based on, just like for compression in columns, it was based on our basically our unsupported length, our length between lateral supports for columns. We have in this bending criteria also an unsupported length that we have to consider. And this is the table 7.5.6.4.3, which is where we get our effective length. And you can see that it's always some number multiplied by either our unsupported length, LU, or a purlin spacing, A, which is a distance between kind of lateral support points on a beam. If I do have lateral support points, for example, I have some purlins along this beam, they are spaced at a certain distance, A, so we can only buckle kind of between those purlins. So then we're going to use A. If I have just a simply supported beam, my unsupported length is simply going to be the total length of the beam. And you can see we have different K factors effectively. That's these numbers 1.92, 1.61, etc., depending on where my loads are, what kind of load condition I have, and depending on whether I'm talking about a beam or a cantilever being any part of the beam that has a free end that can buckle sideways like this. Okay, so We'll see example of that when we do our examples. Basically, any loading in this table is just any kind of loading that does not fit into one of the other categories. So if I have a loading condition that doesn't fit into uniformly distributed load, concentrated load on the center, concentrated load at 6th points, etc., then I just use the default value, which you can see is a worst case value of 1.92. A longer effective length here is going to make a higher slenderness, which is going to make our beam more likely to experience lateral torsional buckling. So the unsupported length is, as I said, either LU or A like this. Okay, so my LU is either, as I said, the total length, if I only have supports at my point of bearing, or the distance between purlins if I have purlins along the length of the beam that are laterally supporting the compressive edge at those points. Now, if my beam, for example, goes over a support, say it's a multi-support beam, so I have a support in the middle, so that at the middle here, I have actually compression in the bottom instead of the top as I go over a intermediate support, then I can't consider my purlin spacing anymore, because now my purlins are restraining. If my purlins are on top, they'll be restraining the tension side. So then I would have to consider basically the full length of the section of the beam that is in a negative moment when I'm considering my bending. And you can maybe draw a picture of a moment diagram where I have 3 supports in order to convince yourself that what I'm saying makes sense. Okay, so now that I know how to calculate my unsupported length and therefore my effective length, LE, from the table 7.5.6.4.3, and therefore my CB, which is my slenderness ratio, going from bottom to top here, now I can calculate my KL. And my KL has 3 different cases. And these 3 cases depend on what kind of mechanism for buckling I'm experiencing. So for a short section where I have a low slenderness, then my beam is likely to not fail by lateral torsional buckling. It's going to fail by either crushing of the top or tension failure of the bottom. And for those, I do not have any buckling, so I don't have any KL. My KL equals 1. So that's one criteria. For short enough sections, for sections with small slenderness, because of course the L, our L effective, highly affects what our slenderness is. And then there's a second category, which is an intermediate category where I have kind of what I would call inelastic lateral torsional buckling, where I have a combination of crushing or a tension failure and also elastic lateral torsional buckling. So both effects are happening simultaneously. And then I have a third regime for KL, which is where I have basically pure elastic lateral torsional buckling, which looks like this. My ruler here is having pure elastic lateral torsional buckling. That means it buckles, but then nothing happens to the material. Everything remains elastic so that when I let it go, it just comes back. Okay, and those are where I'm going to get the highest reductions for KL, but I'm not getting any inelastic thing happening. So each of those different cases has a different calculation for KL. So starting with the no buckling case. So when I have a short beam or a beam that has a low depth to width ratio and my CB happens to be less than 10, so this is my slenderness for bending, for lateral torsional buckling is less than 10, then my KL is just equal to 1, which means I'm not getting any lateral torsional buckling. Okay, so this is the part of the response where I have a medium slenderness. So what I'm having is basically a combination of lateral torsional buckling and member section failure happening together. This is why I call it inelastic lateral torsional buckling. So if I had this and I had the lateral torsional buckling failure and then I let go of the load, I'm still going to have some residual deformation in the beam. Like it's not going to spring right back. And so that's why here I have an equation that is bounded basically by 10 on one side, which is below which I had no buckling, and a parameter called CK, which is the slenderness at which I transition between inelastic lateral torsional buckling and totally elastic lateral torsional buckling. And you see here the strength FB is coming into it, which is an indication that we are having some inelastic effects happening here. And this FB is the same FB that we had before, which is capital FB, which is our small FB times KD times KH times KSB times KT. Oops, just like usual. KT. Okay, and I have an equation. If I fit into those bounds for CB, then my KL is going to equal this fairly simple equation that is a function of both CB and this limit value CK to the fourth. Okay, now the last category, which is totally elastic lateral torsional buckling. Okay, so this is the last regime between CK, which is the borderline between inelastic and elastic lateral torsional buckling, and 50, which is a limit on slenderness for beams, which we will talk about in a second. And if I fit within that range of CB, bending slenderness, then I get this KL 0.65 EKSEKT. That is a Young's modulus value modified for the fact that Young's modulus changes if the material gets wet, divided by our slenderness times FB times KX, which you may recall is our curvature factor, KX, which we haven't really talked about in detail, which will be 1.0 if my beam is straight. Okay, so then what happens if CB is greater than 50? Then the design is not permitted. So CB equals 50 is a limit on acceptable slenderness, and if I don't fall into that category of CB less than 50, then I have to change my design by either changing my beam size or changing the restraint conditions, both of which would change CB. And this is just like the case that we had for column buckling design, where we had a limit on CC, which was also happened to be 50. So that's it. Now, once I calculate my KL, I can take that and sub it all the way back in. So I've got my KL for lumber or glulam using the lumber lateral stability factor or the glulam lateral stability factor. And I come all the way back to my equations for MR for bending resistance. And I can now sub KL in there, and we also saw how to calculate KZBG. The section modulus is just I over Y, as we talked about. For rectangular sections, that's BH squared over 6, which we'll see in the example, and FB is our strength. So now we have everything that we need to know to calculate bending resistance for beams. And in the next video, we're going to have an example after we talk about deflection criteria for beams.